Hello and warm welcome to SAP on Azure podcast. Today is December 12th, and with Holger and myself, we'll talk everything and anything related to Microsoft and SAP. Hello. Today we have some really interesting topic, but just before we start everything, we have just some sad news. A dear colleague of us, Ralf Klahr, is kind of recently passed away, and he was a guest here, guest speaker, and it really shook us a lot. He had a wonderful way. He was excellent person, and he had also very funny way how to present the stuff. And he always loved to share the recipes with us. You know what he was a big fan of cooking and eating. So, in tribute to him. We also decided that Momin will share also just before we start everything one recipes from his side, so in remembrance of him. So Momin, you I think you prepared some nice stuff.
Absolutely. Yeah, no, I know this was Ralph's sort of tradition where he used to bring in recipes, and I sort of got into that, and I always exchange recipes with him and things like that. So some recipes are, you have maybe some friends over, you want to really impress them with a great meal appetizers. This is not that recipe. This is code red emergency. You have a meeting in 20 minutes, or you're driving home, your kids are screaming, everyone's angry and screaming, they're hungry, and you need a quick fix. And this is my tuna sandwich recipe. Quick can of tuna in a bowl, mayonnaise, diced celery. Some people like mustard, salt, pepper, toast some bread, lettuce, tomato. And the secret is taking chips on top of the tuna, crushing it like this, and you can feed your whole family. And this meal has a lot of protein, so it'll hold you till dinner. So this is my quick recipe in case of code red emergencies.
Momin, this is amazing.
Yeah.
This is
and I
amazing.
believe you already tried with some customers, meaning family and friends, right?
Yes.
And it worked. Yeah, which is a proven
on angry customers. And what's interesting is you give them the sandwich and temperature cools down.
Yeah, super.
This is great, and really an amazing tradition, continuing and remembering, honoring the legacy of Ralf, which obviously we all miss because he was an amazing colleague, and I think he really passed away very unexpectedly now, and it was really sad to hear. But Momin, I love it. I think this is such a great idea to also remember him via these recipes. So thank you so much for that.
Thank you. Yeah.
Yes, I think I just wanted to add to that Ralph was one of the best and the finest, distinguished engineers I've come across in my career, and he contributed a lot to my success. And I think he will surely be and deeply missed by all of us.
Yeah. No, he was larger than life, definitely.
Yeah. With that, I think we'll kind of
we can switch. So basically, the topic is basically the guys. Many customer would run SAP on HANA. HANA SAP system grows, meaning the database grows. Generally, recommendation from SAP is to always go for the scale up. However, that scale up has also the limit. So we have 32 terabyte VMs, but lo and behold, sometimes customer will reach that kind of limit as well, right? So meaning they have to go for the scale out. So we will discuss here about designing scale out system, how about the compute, how about the storage, networking, HA, DR, and for those existing customers which are at the moment scale up and need to scale up and need to migrate to scale out, how to do it, what would be the best way and easiest way. So, but anyway, before we start, let's do a quick intro. Guys, you were guests, but maybe some of audience will see you for the first time. So maybe who would be the first?
Yeah, I think I can start off. This is Abbas and Momin. I'm a principal cloud and AI solution architect, having worked for Microsoft for more than 10 years and covering some of the largest SAP on Azure customers in the retail and consumer managed goods industry segment. With that, I'll turn it over to Momin.
Yeah, first of all, thanks, Goran Holger. I don't know how you guys even do this podcast because you guys have such demanding jobs. You guys do speaking engagements. You guys are always designing things and blogs. So I don't know how you find the time magically to do this, but we appreciate it because it's such a nice platform that's very easy to deliver this great content and really appreciate it. So thank you for that. My name is Momin Qureshi, based out of Atlanta, Georgia. I'm a senior technical program manager and I specialize in SAP workloads on Azure. And I work on the same team as Goran as well.
Yes.
Thank you. So today, so for today, we basically are going to cover one customer case study. This is a Fortune 50 consumer packaged goods customer with one of the largest S4 HANA implementations in Azure. And their journey on Azure, the architecture, and how they scaled over the period of several years, and the migration strategy that we have, going to continue forward with. So with that said, I think we'll kind of go into the slides. And this slide kind of speaks to their, S4 HANA deployments over several years. They started out with an S4 HANA greenfield deployment with a 3 terabyte VM in Azure in 2020, and gradually over the years they have kind of, moved up to 6 terabytes, to 12, to 24, and in September of 2024, they were at the 32 terabyte VMs. We did a podcast on this in the past as well. They were the first customer on a 32 terabyte VMs across all hyperscalers. So, since then they have been on 32 terabyte VMs, but they're growing fast. They're growing at 1 terabyte per month, and they are at currently a 27 terabyte database at the persistent storage layer, of which close to 18 terabytes is loaded into memory, and another 6 terabytes with working memory. They are hovering around 24 terabytes. With the current growth pattern, in next to 4 months or so, they would exceed the limitation of 32 terabytes, and there is nothing more beyond 32 terabytes to actually move up to. So the customer made a strategic decision 6 to 8 months back that they can't just stay on scale up. They need to pivot and go to scale out for S4. And they started working on it. They set up 2 24 terabyte MV3 VMs. And since then, they have been testing for the past 6 months on the scale out. And they expected to go live with the HANA scale out architecture in February of 2026, which is a couple of months or less than 2 months away from now. So this, I think, kind of speaks to their growth, which is amazing to see. In the 5 years, 6 years, they've gone from 3 terabytes all the way to, we're looking at 48 terabytes now with 224s in play. The next slide talks about the compute design. So in this, if you look at the design, the scale-up architecture consists of a single VM within a HANA site. You have 2 VMs across 2 zones, and they have been using the MV3 32 terabyte VMs with 896 vCPUs, 30 gigabyte memory. It does use the MANA drivers, the MANA device, which is the Microsoft Azure Network Adapter as part of the Azure Boost. That really offloads your network and storage virtualization from the VM onto that special driver, special device. And you can see that you get 185,000 megabits per second, which equals to 185 gigabits per second throughput. You have 4 gigabyte in temp disk storage, and then you see that you can have 64 disks you can attach as remote storage. And for the premium managed disk, you have 110,000 max IOPS and 8,000 megabytes per second throughput. So the customer is already running on this with their scale-up architecture, and when they were looking to do the scale-out architecture, they did downsize to 24 terabyte VMs, but fully recognizing that the CPU remains the same, and everything else remains the same except memory. While they go down on memory from 30 terabytes to 24 terabytes, everything else from CPU to network to storage IOPS and throughput, everything is exactly the same. Now, one other consideration we had in a scale-up architecture, we would typically deploy their VMs in zone 1 and zone 2 as zonal VMs. But we realized that when we're doing a scale-out architecture, we need to have the 2 VMs that are part of each HANA site. In the past, we used to call this a master and then worker but the master has now been renamed as coordinator by SAP, so we call it coordinator and worker 1. These 2 nodes, we wanted these to be co-located in the single cluster. We didn't even want that to span across 2 clusters. And keep in mind, within Azure, we have MV3 compute clusters that are deployed in the same data center as well. You've got multiple. So we wanted to be careful. And the only way for us to achieve this was to basically create an empty availability set and pin it to a compute cluster within a desired data center in that particular zone. And that was done by our backend engineering through Momin and team. And then we basically provision the VMs in that availability set to land these VMs in the desired compute cluster within that data center. Also, we associate that with the PPG over here, and this PPG was leveraged by the app servers as well as the central services. Typically, when you're deploying app servers and central services, you could deploy them, as zonal VMs, and app servers could be in a VM scale set, spreading across multiple data centers within a zone. But customers' desire was to have the most optimal and lowest latency architecture, and the only way to do it was to kind of use PPG to force the entire deployment into that single data center.
So because the scale out, in this case 2 nodes, you read the parts of table on one node, read parts of table on another node, and of course ideal is that they sit physically close to each other so that the network latency is really super low, so in order to get the best performance, that's the
Exactly.
Absolutely.
Yes. And the same thing we use over here in the HANA site too. They were placed in a view set pinned to a compute cluster, and likewise in the East US, which is the DR region, we did the same thing with pinning of the availability set in that one. Now, from the compute design going to the network design, we have as Azure load balancer, which is a zone redundant load balancer across zones. That is front-ending the architecture. And in a scale-out architecture, the HANA load balancer basically forwards traffic to the master nodes or the coordinator nodes of the HANA site. So in this case, we have a HANA site 1 and HANA site 2. Let's assume HANA site 1 was the primary active site and HANA site 2 was the secondary site. In this scenario, the load balancer would be forwarding requests to the master or the coordinator node in the HANA site 1, like is shown over here. And in the case that this HANA site 1 were to go down and we perform a failover to HANA site 2, in that case, the load balancer will forward traffic to the master of the HANA site 2. So that's what is there for the load balancer VIP. There is a second VIP over here, which is not documented in this picture, but I'll speak to that, where our customer does use the HANA active read or read replica solution, where they are offloading a lot of the reads to the secondary site.
Okay.
So while the active HANA site is taking on all of the read-write workloads coming to it, but a lot of the read traffic is also being distributed or offloaded to HANA site 2. And there will be a second VIP over here, which basically always point to the passive HANA site's master node.
But that's interesting because you kind of load balance also the capacity load or CPU and memory utilization. You go to the synchronized side on another side for the read, so to say, not burden the primary side. Right.
Exactly, that's the intent, right? I mean, because there was a lot of pressure on the primary side, anyways, even on the scale-up architecture, so that to really distribute the workload, the read traffic is being sent to the passive side.
So basically, the compute is the best way utilized, not just for the HA purpose, right? But also for the kind of scaling and balancing of the load, so to say, as well, for the whole system. Yeah.
Yes.
Nice.
And then we also, from a design perspective, whenever we have done scale-out architectures in even the past, I mean, we have always, used the 4-NIC virtual NIC solution. So we have continued with that approach. I mean, and which is basically you have a NIC, virtual NIC created for your client traffic. So I think your app server communication coming to database, or even someone logging in to the HANA database VM is all coming to the client traffic. There is an internode NICs that's also created for each of these HANA VMs, and this ensures that any internode communication that's happening between the 2 nodes of individual HANA sites. In this case, HANA site 1 has a master and a worker, and while they're communicating between themselves, they'll always be using the internode virtual NIC, to communicate on that one. And likewise, the HANA site 2 master and worker are communicating with each other on the internode NIC communication. Then we have an HSR virtual network interface, and this basically allows the master in HANA Site 1 to basically be able to set up an HSR replication with the master in the HANA Site 2. And likewise, the worker in HANA Site 1 is establishing HSR replication to the worker in HANA Site 2. The last one is the storage virtual NIC that we have, and that is really to allow the VM to be able to communicate to the and connect to the ANF storage. So we do use a mixed storage architecture where the HANA log is sitting on premium managed disk, but the HANA data file systems are sitting on ANF, and so is HANA shared. And that's the reason we need the storage NIC to connect to the ANF storage. The other one important thing which we'll talk in the high availability architecture is that, as you can see, there's another VM over here, which is a majority maker as part of the pacemaker clusters. But we'll kind of, as we continue in the HA architecture, we'll speak to that in detail. We need that because we are setting up a cluster beyond 2 nodes, and that's why we would need that. With that, I think we will move to the storage architecture for Momin to kind of go through.
Yeah, thanks, Abbas. You did a great job describing the architecture, but like we mentioned, this is a 2-node HANA scale-out system. And really for the managed disk, we created the OS disk, the user SAP install. For the managed disk, we do use a Stripe file system, managed disk PV1. One thing to mention here, we do have a flag called write accelerator, which helps with write latency, which is really important for HANA logs. So we use this. And then for the ANF volumes, we use 4 data volumes. We have HANA data 1, data 2, data 3, data 4. So you might be wondering, why do we use 4 ANF volumes? Usually on a system, you see 1 HANA data, but for these size of systems, we needed to distribute the I/O for the large amount of throughput. Additionally, we do have some limitations on the OS that if we were to create 1 volume, we hit some maximum write throughput issues. So we use HANA partitioning, where you can set some settings in HANA, and HANA will automatically write to these 4 volumes, which is a neat way to avoid any kind of write throughput maxes. Go ahead.
If I may just jump here, Momin, actually, Ralf was also working on this topic in the past. I remember. Yeah. So, whereas initially was either you use a managed disk or you use ANF for everything, for HANA data, HANA. Now it's basically also there's a possibility to split. So data on ANF, and in this case, log are on a managed disk. And basically, I remember there was also one of benefits also here that you ANF for the data you use networking path or networking bandwidth, and for the log disk you use managed disk bandwidth, which is a separate one. So
absolutely,
you optimize also sharing of the traffic between the HANA data to network and HANA log towards the managed disk.
No, spot on, Goran. That is to avoid that congestion. And that was, like you said, Ralph's brainchild. Yeah. And we had a lot of, it wasn't easy to get that architecture through at Microsoft. So, but it's we've used it at multiple customers. It's absolutely amazing. One last tidbit on this that we did use from the source system. This customer had limited IPs in their ANF subnet. So we actually in the source system took some snapshots, recreated these volumes. So these new scale-out systems have the same IP addresses as a source system, but we're able to fit it in that limited subnet. So if any customer has that issue, that's also a trick you can use of cloning volumes.
Yeah, typically with the ANF delegated subnets, you don't have a subnet expansion feature at this point in time, so you cannot expand the subnet once it's created, and some of this predates the ANF application volume groups that was used to create these volumes in the past. So you need a lot more IPs than it was there. So you have like a /27 or what for the ANF delegated subnet. So we can expand on that. So you have to make use of what it is there. You could always create a new VNet with an ANF delegate subnet and peer it to this one. But our customer wanted to kind of keep everything in one VNet and and that's the reason this is snapshot and clone approach kind of helped, kind of preserve and leverage or reuse the IPs that were already available, or use and not, kind of try to max out on the IPs that we did not have in here. With that, I think any questions on this? We're going to go on to the next slide. Okay.
Let's talk about ANF volume naming conventions. And Just I'm not going to mention how many years I've been doing IT because being in the Friday mode, I can tell you that when you're younger and you graduate school, you say, I've been doing this for 5 years. I'm like a really senior level guy. I'm the complete opposite now. I don't even like to mention like some of the versions of SAP or anything I've worked on just because people can figure out, man, this guy's really old. So, but naming convention standards are just so important, right? When I look, for example, if I look at a host name of a VM, I want to know if it's a production VM, is it S4, is it some other product? So me and Abbas, when we were talking about this, we have a lot of admins in these teams that they manage many groups. Maybe they're not SAP centric. How will they know what these systems belong to? So just real quick that you can see all these volumes start with HN1, the SID of the SAP system. All these volumes have data that somebody can determine these are data volumes. And you can also see the last part, Mount 001. That means that this is for the coordinator node. Or if you see Mount 002, you know this is for the worker node. And lastly, you'll see that in AZ1 is our primary environment. We do not have an HA marker, but in zone 2, where there is HA, we have HA in the naming convention. So any admin can look at these volumes and know exactly where they go. And I personally have done this in my own experience where I've mounted wrong volumes before and things like that. So having that clear markings, and this is all like right now we just see the slide, but like this took weeks of like deliberation between people and people having other standards and things and coming out with this. But I think this is always such an important piece of like projects that sometimes get overlooked, and it's really hard to retrofit naming conventions and standards. So
yeah, absolutely. You know, when you mention in, I mean, it is super important because these systems are becoming really complex. You
yes,
don't know where it is, and it's so easy to wrongly mount or thinking this volume is for that, but actually it is not. So very, very important topic, and in any, I mean, in any system, but especially in those complex like scale out system, you know, where actually even multiple more nodes that customers are in, more than two nodes, you know. So excellent point, Momin. Yeah.
So on the next slide, this one is really talking about the high availability architecture for the scale out. I mean, so one thing I want to kind of state that the application layer with the central services and the app servers remain the same in a scale up architecture. We're not making any changes to that. All we're doing is that we're basically, instead of pointing the scale up architecture to a scale up HANA database, cluster, we are basically pointing into a scale out HANA database cluster. So in this case, just going quickly over the central services, as you know, they're fronted by an Azure load balancer. We have the ASCS and the ERS whips, pointing to the two central services nodes, and also from a pacemaker cluster standpoint, you have three SVD VMs. That's what we use for the quorum in this, and are spread across the three availability zones in South Central US, which is VM1, VM2, and VM3, as you can see here. And then the app servers are placed in availability set, and that's really coming in from the customer's requirement to have everything in a single data center using PPG. Otherwise, you could, as many other customers have seen, that they could put these app servers in a VM scale set with FD equal to 1, and that gets spreads across different data centers in the same zone, and the latency is low enough within a data center, within a zone, for it to be sufficed. Now, coming to the database side, I think I want to touch upon a couple of things on the architecture on the database side. It's going to be a 2+2 architecture, where we have two database nodes, the master coordinator in DB node 1, and then we have the worker node here, and then we have the master, in DB node 3, and the worker in DB node 4. And because it's an pacemaker cluster architecture which goes beyond two nodes, you have to follow an n by 2 plus 1 formula, which means that you need to have an additional node that what we create as part of the cluster, as a cluster member, 5. And the reason we do it is primarily because, let's say, if South Central US AZ1 is down, if you have these two nodes down as part of that because the compute services are not available in zone 1, then you are left with these two nodes over here. And if in the absence of the majority maker, what would happen is that it's a 2+2 architecture. The two nodes over here do not have enough of a worth to ensure a failover from zone 1 to zone 2. And that's the reason having this fifth node adds as a tiebreaker, where basically three nodes are voting that the 1 and 2 are down, and you can automatically perform a failover. So you need that majority maker available to perform the failovers. Now, one of the things we ran into with this customer, it may not happen with other customers, but good point to note here is the key thing is this customer does use HANA fast restarts. And what HANA fast restarts does is that you basically are holding up, in addition, the row and the columnar data or the tables in memory. Even if the database were to go down, you have the data still persisted in memory, and that allows your database to come up much faster. Rather than taking 30-40 minutes, it's going to come in a lot quicker in a few minutes when you have the HANA fast restart. The customer loves that feature of HANA and leverages that. In a scale-up architecture, what happens is that, let's presume if this was a scale-up architecture, you have a single node here as your primary, and you have a second node over here as an HA. So in that context, what happens is that when you perform a failover from the primary to the secondary, you go from this left side zone 1 to the other side zone 2 pretty quickly. And in the left-hand side, you are left with a database that's an old primary, and typically with the HANA fast restart, there is a defunct process that takes a longer time to clear because your index server has crashed, as an example, and the defunct process takes a longer, like 20 minutes to clear. And then eventually the pacemaker cluster recognizes that and restarts the database. Now, the customer already has worked with SAP, and everyone acknowledges that the defunct processes have a certain time it takes because of the HANA fast restart is loaded in memory, and it has to clear up before the database can restart and resume the secondary HA operations. In a scale-out architecture, what happens is that in the context of this customer, the master node has a larger size than the worker node. As an example, the master node is hovering around 14 to 16 terabytes, and the worker node is like 3 or 4 terabytes less. It's like 10 to 12 terabytes. That's what the sizing is between the way the table placements have happened. So in this context, when you perform a failover, let's say DB node 1 index server crashed, as an example, you immediately fail over to the other side because you're using the SUSE check server, and which is and the SUSE HANA SR and G, the next generation pacemaker cluster resource agents. You perform the failover. The failover works perfectly fine. Your DB node 3 and 4 assume the primary HANA site operations. Everything is good. But resuming the secondary has a problem because now your DB node 1 and DB node 2 are both left with defunct processes because the action on fail is to kill. So the pacemaker cluster attempts to kill the database on database node 1 and database node 2. And when it tries to kill the defunct process because of the HANA fast restart, it's taking a longer time to clear. And it so happens because the master database is a higher size than the worker database, the defunct process clears on the worker node first, and it starts the worker node. And it realizes the worker node is up, but not the master. And then it goes back and shuts down the worker node and starts the master database. Eventually, after defunct process clears, master comes up and realizes the worker is not up. It goes down again, and eventually both of them come up. It takes a good 45 to 50 minutes to resume the HA operations, which is not acceptable. And the customer is not willing to give up the HANA fast restart, which could have solved this problem as well. So the solution to this is that the SUSE recommended was they did provide an updated their next generation ANGI resource agents, which helps. Then the second thing they said was on action on fail, they are basically recommending to switch from kill to fence. So what happens when a failover happens? Instead of the pacemaker trying to go and kill the database on the two nodes, the pacemaker tries to fence the two nodes, which means it restarts the two nodes. Right? When you restart the two nodes, the memory gets automatically cleared, and this has proved to be much faster for this customer. So my recommendation to all other customers is your use case may not be the same. Your master database may not be higher than the worker database. It all depends on your use case. But if you run into this issue where you're having multiple restarts for the master and worker because of the failover is successful all the time. The re-establishing of the resuming of the HA operations is taking longer, and that could be solved by switching that parameter in the global INI file from kill to fence for the action on fail. that I think is pretty much it for the high availability architecture. And for that, I'll kind of move to the disaster recovery, unless you have any questions, Gordon and team.
No. Makes sense. Makes sense. Yeah. And that's a very useful tip, because you also want to, as quickly as possible, reestablish connection to the old primary, just for the safety reasons, right? Just to because you want to replicate, you want to also be able to fall back if there is a need, right? So because you just running on one side, it's one zone only, it's a risk, so to say. So during that time, until you reestablish again the connection to the previous primary. Yeah, makes sense.
Okay. Yeah, Momin onto the DR side.
Yeah, I'll go over a little disaster recovery, and part of this job is like imagination, right? I try to imagine that, in this case, South Central being the primary region, secondary region being East US, what would happen, if there was a flood? What happens if there's an earthquake that completely took out South Central? And I even imagine what happens if Godzilla came and destroyed South Central. What am I going to do? Luckily, we have a DR, and like in Azure, one thing I like about our DR setup, it's very simple. I do like simple technologies where, I feel like the less, complication is, it's easier, especially in those type of crisis moments, DR. So really, for database replication, we're using HSR, HANA native replication. And for most replications in Azure, we use, for Oracle Data Guard, SQL Server always on. We use native replication. We did have to do a lot of tuning with the buffer and some OS settings, but really, even with asynchronous replication, these databases keep up pretty well. For the central services, app servers, we use, once again, ASR, a very standard proven product. And then for the top part here, you'll see the ANF volumes. The customer uses a custom solution, a backup third-party solution that sweeps the file systems and syncs the DR region. One thing to note there, that for ANF, as of present, you can take a volume. You can either do cross-zone replication or you can do cross-region replication. Unfortunately, you can't do both at this point in time. So the customer sort of prioritized cross-zone replication. That was more important. The cross-region, they're using a third-party product. And we have exceptional RPOs. I mean, you'll be very surprised. I think more of it is on the technical validations, the approvals and things. The actual technical piece of the cutover is so quick. And with practice, I mean, that's just confidence that that company has, that in case of even, we knock on wood here, we haven't lost a region, but like, if we were to lose out some kind of major region like that, we have confidence that we'd be up and running.
Yeah.
One thing I would like to mention is the RPOs. I think I kind of forgot to mention on the high availability from a high availability architecture standpoint. We look at the database and the application layer. The RPO is 0. I mean, and the only place we have an RPO of 20 minutes is because of the ANF, because we host our SAP mount transports and interfaces for the application layer in ANF here, and for that, because of the cross-zone replication solution, we have a 20-minute RPO for the ANF. But other than that, it's RPO of 0 in the entire stack. The RTO for this architecture end-to-end from zone 1 to zone 2 is 30 minutes. That's what we have for that. And when it comes to DR architecture, the RPO is 30 minutes, and the RTO is 4 hours in our architecture.
Cool. When I look this, really the most complex scenario that we have, I mean, before the Azure, I mean, even having HA was a luxury. And here is not just the HA, it's actually kind of metro cluster, which is far away, So, and even having a DR, it in the past was science fiction. Simply the costs were too great, just to have that. And these kind of stuff, it's becoming a commodity, so to say.
It really is.
Yeah. And I also start to appreciate more and more the naming convention when I see
Yes,
right.
Absolutely.
Yeah. And the other thing is that also with the ANF cross-zone replication solution having a 20-minute RPO, we're also kind of moving to an architecture. There's a capability that's being developed called ANF ZRS solution, which in a sense, will bring that RPO down to 0, and that's kind of it works as some POCs happening with this customer and other customers. And in the Q1 or Q2 of next year, the expectation is to move to the ANFCRS solution, which will also bring down this RPO to 0. With that, I think the last one is the migration strategy.
Yeah, last one, migration, relatively straightforward. If you look at what we're really doing is the node 1, the source system, we are replicating it to the scale out, and we'll probably kick that off earlier in the week. Once we have the approved downtime on the weekend, we'll shut down SAP, right? So no new orders and processing. We're cut over from the source to the scale out system. Now, in the scale out system, there is one thing that, and I would say it takes about 4 or 5 hours. They are moving tables. They're moving tables. Everything's in one node. We're moving that over to the secondary nodes, certain tables, the HANA database admins will do. And then once we're ready and everything's validated, we'll switch the HANA load balancer to point to the scale out, bring up all SAP, and then just the secondary zone will be replicated through native HANA replication, and the DR will also be replicated. So one thing I would say is, like, back to what you're saying, Goran, that I imagine, and I'm not going to mention how many years ago, but when we used to do this on-prem, I would have to order hardware, and that hardware we'd have to check with the engineering teams. Do we have cooling? Do we have power? The guy would say we don't have floor space. We'd have to rack stack cable it, and you'd be amazed like how quickly things get stood up now with Terraform automation. Things get stood up. I mean, myself and Abbas get requests Thursday evening. Hey, we need a full N+1 environment. We have something going on with this upgrade. And by Monday morning, they have, between the automation, tooling, they are able to create these full environments, things that used to take us months to develop. So the speed of innovation in Azure is just amazing in that sense.
There is one correction on this drawing. I want to point out, and we're creating this slide. We should only have a one load balancer across, not two load balancers here. This one load balancer basically starts with pointing to DB node 1 and the DB node 2 over here, and this should basically be pointing, eventually when we failover, it points to the DB node 1 over here and the DB node 3 over here. We don't need this whole load balancer here, so kind of, please ignore this.
And I'm just thinking from a migration complexity, it's kind of relatively simple, because you use an HSR, downtime is really super minimum, and everything is kind of resyncing, so it's more on the database side, so to say. And
you have that source system still in place, and something goes wrong, we can fail back pretty quick. So I just think these projects, like, there is safety and speed now that these type of customers can't afford large downtime. So pretty neat in that sense.
With that, I think we'll quickly go to the demo environment. I think the demo environment will look like this. It's pretty straightforward. It's been built out from a scale out. We have 3 zones, and it's really focused on the database side. We have 3 SBD VMs, as you can see, with this IP addresses 10, 40, 20, 11, 12, and 13. And then we have the HANA Site 1 and HANA Site 2, which has 2 VMs. For HANA Site 1, VMO1, VMO2, and the 4 NICs, so the virtual network interface cards that are associated, and all of the IP addresses for those. I mean, like you can see, these are 10, 40, 20.4, 21.4, 22.4, 23.4 for the client, inter, HSR, and storage. And basically for VMO2, it's all .5s in the end for the last octet. And VMO3 is .6, and the VM4 is .7s, and we have the VMO5, which we should have named it majority maker, but when we were creating the demo, we just call it VMO5, so it's a majority maker. With that said, I know we've been kind of extended out, so we'll just quickly try to do a quick 5-7 minute demo to show you what we have. So what I've done is on the left hand side, that whatever picture for the demo was, I kind of put this over here. This is really the demo environment, and kind of to show you a little bit quick, these are I'll kind of focus on these are the IP addresses, and what you're seeing is that from a cluster standpoint, as you can see, just to highlight on here, you basically are actually seeing that all of your nodes are online. The VMO1, VMO2, VMO3, VMO4, which is at the HANA Site 1 and HANA Site 2, and the VMO5, the majority maker, is online. The Sony SBD can run on any one of these 5 cluster members. It just happens to be running on VMO1 at this point in time. We also have the Azure Health event, enabled on all the 5 nodes. That's why it says it started on all the 5 nodes. And the HANA topology agent currently is running as expected on VMO1, VMO2, VMO3, VMO4, because this really is looking at the HANA topology, and that is only running, should be running on only the HANA nodes, the VMO1, 2, 3, and 4, and rightly so, it's stopped on VMO5. We don't want that to run on the majority maker. And then we have currently the HANA site 1 as the primary, and the master is being depicted as the VMO1, and of course the worker nodes or slaves are kind of shown as VMO2, 3, and 4. And VMO5, we don't want this to run. That's the reason by design it's stopped. In the past, when the pacemaker cluster deployments used to happen, sometimes these agents would actually incorrectly run on the majority maker, and that's been fixed in a documentation and as well. And likewise, you have the HANA file system, which basically looks at the HANA shared, and it's running rightly on the VMO1, 2, 3, and 4, and not on the VMO5. We also have a load balancer with the IP address, and that's basically that IP address is a floating IP address, and rightly so, it's currently running where the master is, so it's running on the VMO1, and also the netcat port is running on VMO1, listening in for the traffic. This is the ideal architecture. And before we perform a failover on this, I just want to kind of quickly show something as well. If I do an IP config A on the IP A on this one, you can see that your IP addresses for the VMO1, 1040.24, they are all listed here. So this is your network, 1040 network, which is basically your client network. You have your internal network. You have the third one is the HSR network, and then you have the last one, which is the storage network listed here. So all four ETH0, 1, 2, 3 are listed, and you see that your load balancer address 1040.20.15 is also shown here, is running here because your VMO1 is the primary over here. Yeah. If you were to fail over, it's going to go onto the VMO3. It starts running over there. The other thing is ETH0, ETH1, ETH2, and ETH3 are your primary interfaces, next. And as you bring up the VM, you have the ETH4, 5, 6, and 7. These are accelerated networking interfaces that get teamed or bonded to the primary interfaces. As example, ETH4 is bonded to ETH0. You can see that over here it says that it's kind of going to ETH0, and ETH5 is going to ETH2, and ETH6 is going to ETH1 here, and ETH7 is going to ETH3. So it kind of shows you the mapping of those accelerated networking interface cards. Now I think the other thing is we can do is that now that we know how this is set up and running, if I was going, I can just trigger a quick failover to show you. So if I go to my VMO1 and log in as SID ADM, you can see that right now, when I run a Python command, let me do this actually. Let me clear this up a little bit and kind of make it easy. So if you do run this command, you can clearly see that everything is up and running, everything is synced, and from the primary HANA site to the secondary HANA site, and the database, of course, is running and all looks good. And what I'm going to do is then you're going to run a command called HDB. Give me 1 second. HDB kill -9. And we're going to watch this kind of trigger a failover. So now you see that this is kind of killing the index server over here. And as you can go onto the VMO1, you will start to realize that in a few minutes it's going to switch over from the HANA site 1, where VMO1 was the primary active, and VMO2 is going to switch over to the HANA site 2. And once we do this, I think, we can probably conclude the demo after this. Yeah.
And basically, both nodes will move, of course, to the
the primary
1 and 2
the
to the 3 and 4, right?
Exactly. So, and in a scale-out architecture, it's by design that whenever you have a failure of the master node or the worker node, irrespective of what happens, it doesn't try to restart the server on the same node, because it's by design the SUSE check server, pacemaker cluster resource agent that we set up. Like as you can see, the first thing that's moved is the resource IP and the netcat port. They have moved to the VMO3. It's of course calling out that the VMO1 is having the issues, and that's the reason it's moving it. It's also going to now move this, is recognizing the VMO1 has failed, and it's going to basically look at promoting VMO3. As you can see, the VMO3 is coming up, and in a few minutes, you can see that that this whole thing is kind of taken over. The other thing I think real quick I wanted to show the team was around the give me 1 second if I could look up. While this comes up, I'll show you. Okay, give me 1 second. Yeah, I think I'll probably go to another VM to just show you quickly. Maybe we can do this here. Actually, I'll go here to the VMO1 here. Okay. If I go in and just type in and look at the global.ini files for real quick, you will see here that your internal communication is configured correctly to the 1040.21, network. I mean, the internal network interface, as you can see here, like what it is. I mean, the 21. If you look at 1040.21 is your internal network, and then also you look at your HSR communication is kind of system HSR is kind of configured to 1040.22 network, which you can see here, which is the 1040.22 is nothing but your HSR communication. And then these two are your resource agents, which are NG resource agents that have been created, which is the HANA SUSE check server. And here, as I said,
Cool.
the default is action on lost equals to kill, but you can change that to fence, so that you can overcome that issue we were running into. And the other one is the SUSE HANA SR is here. Now coming back to over here, you should be able to see that that yes, you see that this master is VMO3 and the slaves are VMO24, and it's going to slowly clear this up. What I'll do here is that I'll just go and say resource cleanup so that we can clears up this, so that you can bring up the last one over there. In a second it'll do that, and you should be able to see that that clear up in a bit. So that's the one thing we wanted to kind of show you in this file. There's a CRM config file as well. We can I wouldn't go into the settings right now. I think we don't need to. I mean, this is going to just clear up in a second. Just waiting for it, to kind of clear up. Also, the Python thing you can see here. I think now we are going to run the Python command, not on the VMO1 here. Let me just close this. The Python command will be run on the VMO3. So just copy this command, and I'll just run it on the VMO3, which is the primary. If I go here and if I do this, you'll start to see that this thing is slowly becoming clear, and everything is now looking active. It's reverse the replication and all that you can see here. And if I were to go on CRM3, and just do a CRM mon here, we can do it on any cluster node, by the way. You can see everything is clean now. Your architecture has moved over to the master is VMO3. All the slaves are VMO1, 2, and 4. And everything is looking good with VMO3 over here. The same thing will show up on VMO1 as well. It's cleared the operations. And if I go and run the same command here, you see that everything is looking good and clean. No failed actions or anything of that sort. With that, I think we can conclude the call, Gurun, if you prefer.
Yeah. I mean,
I can stop sharing.
Yeah, just to mention, great session. These are really the most complex system you can have in Azure, really, and there's always a need to demonstrate in detail how they work and how to reflect it. And just to mention that whatever you do and show, it's based on your real life experience with the concrete big customers. So it's not just a theory, but basically it's
really working.
Right.
This is the actual design that's going live in February of
Correct.
2026. Yeah.
Correct. So actually everything what you said, it's proven on a customer side to work, and it's properly designed. So thank you guys, really very helpful. And of course, we have expectation, both Holger and myself, you will come again with the best practices and learning from a customer side to share it again, right?
Absolutely.
And new recipes from you, Momin.
Absolutely.
Yeah, there you go.
Yes,
Absolutely.
correct.
Absolutely.
Super.
Yes, quite a few up his sleeve.
Excellent.
That's right.
But now put to another Ralph's level. He was having very fine tuner.
There you go.
Yes.
Thank you, guys.
Perfect. Thank you so much.
Thank you.
You guys
See
are
you.
awesome. Thank you
Talk
so
to you
much.
later.
Take
Bye.
care. See you
Bye-bye.
guys. See you, Abbas.